Session, early development of the FFT algorithm. My name is Jim Cooley. I'm formerly of IBM Research, retired recently. I'm at the University of Rhode Island, Department of Electrical Engineering. I'll introduce my fellow speaker, John Tukey. John Tukey was Associate Executive Director of Bell Labs Research from 1945 until retirement in 1985.
I didn't start in that title.
No, you didn't start in that title, but you were at Bell Labs. He started at Princeton University. His title was graduate student in 1937 and became professor. He's professor emeritus in statistics, and he's honorary professor of science emeritus, Princeton University. Well, I'll start off. I like to compare the FFT, or the discovery of the FFT, with the other great event which we're celebrating this year. It's Columbus, discovering America. Again, saying discovering in quotes because America was discovered by others. And we say what was unique about Columbus, and why do you celebrate the discovery of America? Unless you're a Native American Indian, of course. But we celebrate it because it came at a certain time in history when the technology had developed, when ships were built that could cross the oceans, commerce had advanced, Europe was overpopulated. So Columbus is the peak. The thing we're celebrating today is something like that. We're celebrating an event which was the publication and the transactions of a collection of papers on the FFT. The paper on the FFT, which John and I put out in 2 years before, 1965, and then this special issue became something like the discovery for everyone else, and it came at just the right time. So we'd like to make some comments, sort of personal comments on our own contact with this, tell how this developed. Well, my first association with John was when I was at the Institute for Advanced Study Computer Project, the computer built by John von Neumann. And John was the professor at the university who was the liaison between the university and the computer project. And we had planning sessions every so often, and John came over and was like consultant. But he brought a problem over in spectral analysis, and he was developing what is now known as the Blackman-Tukey methods for spectral analysis. Now, as you all know, the Blackman-Tukey method is a way you take long strings of data, you do an autocorrelation or cross correlations, and then window this, and then with relatively few lags, and in this case it was 30 lags, you do a Fourier transform of 30 points. Now, this had many important properties, but one of them was that you avoid large Fourier transforms. So this is a bit ironic. Our first contact was working on avoiding large Fourier transforms. Well, I'll turn to you, John.
Right. Well, from my point of view, one of the things that was there was the technology for looking at some of these problems, particularly geophysical problems, where you had to think about the statistical aspects as well as the frequency aspects. When I tried to put something together to say today, it seemed to me that the thing to do was to focus on the decade of the 60s, and I was fortunate enough to get hold of some background information, which I'd only heard referred to, having to do with what around Lincoln Laboratory and other places were known as Butler matrices. This was essentially a way to put a Fourier transform on a set of equally spaced antennas and thereby produce a beam that went off in a different direction depending on which of the feeds you used. It was invented by a man named Jesse Butler in 1960 or just before. He produced a 4-element array at 3 gigacycles And then the people at Lincoln Laboratory spent a very busy weekend and produced an 8-element array at 900 megacycles. There will be, for those, and I think there'll be copies enough to go around by then, there will be some one-page souvenir sheets that have an outline over time on one side and references on the other. So, anyway, 61, there were some papers in the literature. 62, there was a paper by Bill Delaney reporting on careful study of a 16-element array. If those of us who worried about numerical calculation had known about that at the time, maybe that would have triggered us off and maybe it wouldn't. But it was essentially the same technique. The twiddle factors corresponded to phase shifters, and the multiplications corresponded to hybrids and other combinational devices. The first thing that I can comfortably anchor is a set of notes that were taken by James Thompson for a course of mine in the spring of '63, which were eventually published in the first volume of my collected works. Those had the basic idea of doing a factorization and doing things on one side and then doing them on the other. While this was going on, or shortly thereafter, Dick Garwin and I were both on the President's Science Advisory Committee, and which met once a month. And we always used to sit together at the end of the table, maybe because we were two of the junior members of the group. And Dick saw me scratching away, wanted to know what I was doing. I told him something about this, and so he took some notes and took them away. And this is what I would refer to as the double plane. Not Tinker to Evans to Chance, but Tukey to Garwin to Cooley.
Well, Dick Garwin came down to the computing center at the at Yorktown Heights, where I was had just started in 1962. I think this was around 1963. Research then, we could do anything we wanted to do, and I was doing what I thought was important until Dick Garwin came in with a yellow pen, just like this, the kind of thing we used, and he had n is equal to a times b on this. And he said, now if you take your Fourier series, and he wrote John's notes here, W is equal to e to the 2 pi I over n, and then write the Fourier series and use this factorization. You can write the series as a series of subseries. And then if you wrote on the bottom, if you iterate on this, you can do a Fourier transform in n log n operations. Well, Bill Doran, head of the computing center, said, well, I don't know if this is important or not, but Dick Garwin is. So let's do something about it. And I put it on the back burner, actually. I worked on it in my spare time. Dick Garwin was prodding me every so often. He told me he had a problem of a three-dimensional array of spins of helium-3 and wanted to see if there were periodicities, and I could program that. Well, I programmed it, and thinking of very large arrays, and you know, we had small memories then, and I programmed it so that we could overwrite the data with results. You didn't need any extra arrays. It saved storage. It also saved forming two addresses, so you had to compute only two addresses for the source and then two addresses for the result, the same two addresses, so it saved computing addresses. The problem was that the result came out in bit reversed order, and then I worked on bit reversal. Gave the program to Dick Garwin. He started publicizing it, and I wrote up some notes on telling how it worked. And one day when we had a seminar and they thought it was about my turn to speak, I couldn't find anything really interesting to talk about, so I told them about this. There happened to be a lawyer in the room at the seminar. Now, IBM doesn't usually have lawyers at seminars, but this was a lawyer who was interested in mathematics. He was mathematically trained and came back after the talk and said, there may be a patentable idea in this. We should look into this. And he got together with other lawyers and they decided what to do with it. They said, this might be patentable. Now, IBM wasn't interested in having patents. In fact, IBM was interested in avoiding patenting software. So their strategy was to put it in the public domain. IBM wanted software to be freely distributable, and because it helps sell computers. So they said, to put it in the public domain as an invention, you have to have a device. So the lawyers had Sam Winograd and Ray Miller design the device and told me to write a footnote to the paper. And I said, well, we have no paper, so write a paper to go with the footnote. So I gathered some of the description of this method that I had for the program and sent it to John and said, would you like to be a co-author? We have to put a paper out on this. John agreed, and this went back and forth, and we finally had a paper. I sent it to Eugene Isaacson at the Cooley Institute, where I used to work before going to IBM, and he was an editor and had it published rather quickly. In about 8 months. It came out in August of '85. Well, my previous 65. Gee, 20 years more or less. What's the difference? Well, it came out in '65. Thank you. I had a few papers published before that, and I was always overstocked with reprints. Nobody ever wanted them, so I didn't order any reprints for this. But the paper came out, and then some responses came. I didn't consider it very important. Certainly Garwin was telling me it was important, but I wasn't quite convinced. I was first convinced when Tom Stockham called me from MIT, and he said, oh, gee, this is marvelous. You know, we can use this to compute convolutions. And I had never thought of computing convolutions, frankly. And I called back to talk to Tom again one time, and I got Charlie Rader on the phone. So I got to know Charlie, and we talked about FFTs. Charlie got very interested, and he got a student, Norman Brunner, very interested. And Norman became almost too interested. He almost gave up working on his PhD, writing FFT programs. And incidentally, recently I was talking to people in crystallography, and I asked them, what Fourier transforms are you using in there? He said, well, they were written by Norman Brenner. No, that was around 1965 or 66. Those programs are still being used. Well, let's see. Then the lawyers, though, they said, where did John get this idea, and is it new? And I called up John, and he said, well, you can look at Yates. It's an article on n factorial experiments in the Imperial Journal of Soil Research in 1937. In that paper, he had the n factorial experiment was to take n types of fertilizer. And if you form a binary word, and if you use the fertilizer, you put a 1 there and a 0 if you don't. Then you try all combinations. Then you have all combinations of the results of this fertilizer. And then you want to take all sums and differences of this, which meant multiplying that vector by a large matrix with 1s and 0s. And then instead of doing a big matrix multiplication, Yates said, well, let's do a successive doubling method, which was something like the structure of an FFT. It's ironical that later on, after the FFT, people started looking at Walsh and Hadamard transforms, and they said, gee, you can compute these with an FFT. In other words, they went backwards to the way it was done originally. Okay, referred to I.J. Good, but I checked on I.J. Good's papers, but he had an algorithm which required that the factors of n be mutually prime, which meant that you couldn't choose them to be as small as possible, but making them small was what made the algorithm fast. Now, of course, the I.J. Good algorithms are used in combination with FFTs, but the point I'm making now, the FFT was, these papers did not lead to the FFT. The idea of doing the factorization with arbitrary factors was original with John. He invented the idea. As we'll show further, it was invented several times by others. Another Philip Rudnick wrote to me and said, oh, I got that idea from Lanzow's paper, published in 1943 in the journal Franklin Institute. And Rudnick had written a program in which he actually did this iteration. And Rudnick's program, I guess, is really the first electronic computer program using an FFT. Now, Lanczos described the method. Now, here's another irony. He described this method saying that they had some measurements of reflections of X-ray reflections on a liquid, diffraction experiments. You have the record, and you sample this, and he said you want to find the Fourier coefficients. Now, there were two important sources of error. One was undersampling. Another source of error was just making a mistake hitting the keys on a desk calculator. So to find out if he had any errors, he said, well, let's do another sampling at the halfway points. So that's what we regard as the decimation, sampling first on the even points and doing a Fourier transform, then do the same thing again, but doing it on the odd numbered points, and do another Fourier transform. The second should be the same as the first, except for the phase shift, which is the twiddle factor. And if you say, well, an improvement is the average of those two, then that's just the sum of those two, which is 1/2 of the familiar butterfly. Now, you have twice as much data, so you should get twice as many frequencies, and where do you get them? And if you do the algebra, they come from the differences of those two quantities, and that is the ordinary radix 2 butterfly. Well, Lanczos then said in this paper, this was new, he said, it wasn't done by Runge. I mistakenly said in an earlier paper it was in Runge. When I looked in Runge, Runge actually had it, but Lanczos didn't know it. So Lanczos also invented it, and Runge invented it. But Runge, in his final thing, he said, well, you can iterate on this. See, now that was important. He knew you could iterate. You could do it 2 or 3 times. So, and that was it. He published another book later on Fourier analysis and only mentioned the method in the footnote. Now, I gave a talk at Yale once, and he happened to be in the audience in the late 60s. And I said, why didn't you publish this and make a report? It's a very important idea. He said, well, N wasn't very big. And all of these other tricks he had, this A-matrix method, they used the symmetries of the sines and cosines, used trigonometric relations to reduce the computing. And the amount of computing you saved by using this was not much greater than you did. So it didn't get much emphasis. Now, that's what I mean by saying the idea hadn't come of time. It had been discovered, rediscovered, and as you've seen in the ASSP magazine, it went back to Gauss. So that was the early history. Okay, now let me go to 7.
I think it's mine.
Yes.
Right. Now, one thing I didn't say previously, should have. Jim tells me everybody wants to know why this was thought of. I didn't have any specific memories, but I look back at these notes for Statistics 596. And there's a lot of consideration in there going back and forth between the discrete and the continuous. And in terms of what was there, I think the right thing to say is this was the only obvious thing to do. It was obvious that you were doing sampling, and if you wanted to start from a set of samples, the only obvious thing to do was to subsample the sample. So maybe that accounts for why it was invented so many times. We had hoped that Gordon Sandy was going to be here, but he isn't. I got him to put down a few things on paper. Let me read some of them. In 64, 65, Gordon Sandy was a freshman graduate student at Princeton, interested in time series analysis as a result of a summer job and reading Blackman and Tukey. Professor Tukey was away in California during the spring semester. Sandy read the Math 596 notes, now available in the collected works, and worked his way through the typos and used it as an excuse for learning Fortran 2. The result was a not-in-place FFT on the 7094. An immediate application was to try to do spectrum analysis. 3,500 points for 500 legs was about the standard amount of smoothing for the indirect method used then. The new method was a lot faster. At this point, Sandy obtained a copy of the Cooley and Tukey manuscript, which described an in-place algorithm but gave no applications. And the two developments had led to 2 technical variants on the factorization. Recall that the IBM 7094 was a, quote, big computer, but only had 32K words of memory, so memory is very much of a concern. Sandy prepared a manuscript which was typed at his summer job at the Defense Research Telecommunications Establishment of the Defense Research Board of Canada, where he worked for the summers of 63, 64, and 65. In the summers of 63 and 64, he spent time doing power spectra with the slow FFT. That may have helped motivate him. So he sent a manuscript to me about May or June 65. This circulated around, and Gordon had been emphasizing the reduced cost for the lag products for the autocorrelations or autocovariances. And as he says, Tom Stockham also made the connection. And then W.M. Gentleman, who also comes from southern Alberta but did not meet Sandy until both were at Princeton. Gentleman and Sandy produced a paper called Fast Fourier Transforms for Fun or Profit, which has on the one hand an error analysis of the FFT showing that you gained as much in error as you gained in computing speed, and a variety of implementation pragmatics, as well as a collection of applications and a table of the correspondence. The major issue at that time was that the finite discrete Fourier transform was regarded as an approximation. On many occasions, Sandy received kindly advice that he was being rather foolish for a mathematics graduate student, in particular, to call this, quote, thing, unquote, a Fourier transform when it clearly was no such thing. Such advice usually came from professionals who were users of time series analysis in various contexts. Comments that it was a, quote, real Fourier transform, but for an unfashionable group with no interesting mathematics, i.e. it was all finite sums, didn't seem to cure the situation. Submission of an algorithm to the CACM algorithm section drew a rather condescending letter about how programs of such repetitive structures were not appropriate for such a serious forum, even if the programs were correct implementations. So this gets us through about 66, and we'll go back to Jim for a brief mention on the Arden House symposium.
Yes, well, as I say, we're celebrating the transactions. We should also celebrate the first Arden House, which is an Arden House on FFT. This was a somewhat remarkable workshop because it was a workshop because where people worked, people did things. We collected people from everyone who was interested in this, and it was strange. You say we're going to collect everyone who was interested in FFTs, and we put them in a house which was limited to 106 people. Well, how big would that house have to be today? Well, we invited Gordon Sanday, we invited some people from IBM, and of course Tom Stockham, Charlie Rader, Norman Brenner, and I'm sorry, I'm just trying to remember names. I don't feel offended if I've left you out. But they're all names that you're very familiar with. There was a woman in France, Janine Cons, who called me up when the FFT paper came out. She was very excited. Her husband had built, Pierre Cons is a famous French astronomer. He built a highly accurate interferometer which measured reflected infrared radiation from planets. And he got records of 512,000 points. And I said, well, you don't really need a Fourier transform of 512,000 points. You can decimate it or smooth it or something. She said, no, he wants every point. And her job was to program this. She was head of the computing center at the Paris, University of Paris, I believe. So she came to the workshop with her assistants just to do this. Now, of course, the array was 512,000 points. The machine was a 32K machine. So Norman Brenner and she got together and they worked out ways of blocking the FFT. Now, here's a nice, interesting point about the FFT algorithm, and many of these complexity theory algorithms we develop today. You break a big problem into little problems with this divide and conquer strategy to reduce computation. But the breakup also breaks it up into pieces which can be done independently. And this is what Norman did. You just break it into blocks. You know, something like Lanczos. He said you can do two Fourier transforms. One operator does it on the even-numbered points, the other one on the odd-numbered points, and they can work independently. It's kind of the same idea. You break it up into blocks, and then you bring the result of these blocks in. So maybe you transpose them if you think of them as matrices. Well, at the end of the workshop, she had the whole thing worked out and went back to France. They ran the program, published it, and she sent me many years later an atlas. It was this wide, this high, like that. An atlas of the spectra of all the atmospheres of all the planets that he had measured. A few years ago, they invited me to a conference in Austria where they were celebrating 3 big events in Fourier spectroscopy. And one of them was applying the FFT to this interferometer measurements. And it's now built into all these machines that the exhibitors had in their hall. Well, that was a rather interesting workshop. Again, I say there was a variety of people. There were heart surgeons there who were programming FFTs for monitoring patients in post-operative care. Many others. And a lot of work was done and a lot of things were developed. A second Arden House came 2 years later. Now, I'd better check with Larry Rabina. It's approximately, we had them approximately every 2 years until 1976. A second Arden House, we talked about the FFT. Dick Garwin came to this, and he made a very important point in his talk. When he was handling this, he was facing the problem of an important algorithm which has to be publicized and disseminated and developed. And he had previous experiences where he was frustrated by an inability to get an important idea out. And he said it wasn't going to happen again, and he worked very hard to do this. And then he talked about the problem of publicizing and advertising and developing an algorithm. But this is where this society came in. You see, when I was invited to join the committee, the DSP committee, as Larry Rabina wrote in the history of our society, the people in this society used to be loudspeaker designers, and that had gone through a sort of a research phase, and it was petering out. And the society was kind of running out of things to do, for one. And at the same time had some very energetic people who were getting into digital signal processing, mainly the people at Bell Labs, MIT, some at IBM, and so on. So the society sort of collected just the right people and at just the right time. And I think more than any other group has advanced the FFT algorithms in their implementations and development. And as you see from the ICASP here, which has been regarded as a descendant of these Arden houses, you see how much that this society has done with FFT algorithms. One of the things the society did, of course, was to publish in the magazine this very important paper, Heidelberg and Burris and Johnson, on going back to Gauss. And they recounted the stories of many people who had discovered an FFT algorithm and used it, perhaps, said something about it, and no more. I can go back to a few more of them. Dick Garwin himself, he was then at a little laboratory at Columbia University called Watson Lab, not to be confused with the big research center in Yorktown, where I was. He asked Llewellyn Thomas, a professor there who, just by coincidence, happened to have been my PhD professor. He asked him if he had ever seen this idea before. And well, Professor Thomas said, well, yeah, I did something like that a long time ago. He had a very large Fourier transform to compute. And at that time, this Watson lab had punch cards and a multiplying punch and a big tabulating machine. And he had to compute the Fourier transform on this. He said, well, how did you find out how to do it? He said, I just went up to the library and looked it up in a book, and it was there. You know, he looked up a book by Peter Stumpf. And Peter Stumpf had this book, Periodogram Calculations, and he had, it looked something like recipes. He said, well, if you have n equals to this, and then we had columns of numbers, you take this column, add it to that, take this column, subtract it from that, then you multiply it by these, and all through this he used the symmetries of sines and cosines, something like Lanczos, Runge, and so on. But in several places he derived the procedure by doing a doubling or tripling algorithm. He just didn't write it as an iterative thing, just to derive the procedure, and then again he had this like a spreadsheet method. Runge was doing the same thing, and in fact, by the way, I could have brought it, but someone gave me some of the templates that Runge used. He had cardboard and punched holes in it, and those holes exposed elements in these columns which told the operator which numbers to multiply and add. It was kind of interesting. But in Peter Stumpf's paper, he had in there several places, well, here's the way you do this with a certain number of points, and then he showed one place where you can double, which was essentially an FFT doubling, and there was a tripling algorithm. Well, Thomas looked at the tripling algorithm, and he generalized it, but then he made the assumption that the factors were mutually prime, because that then eliminated the twiddle factor. See, with our FFT algorithm, as you know, from one iteration to the next, in between, there's a multiplication by W to a power. He eliminated that, and that made it simpler. Now, that was important to Thomas because his FFT was on stacks of IBM cards, and you had to put these IBM cards through a multiplying punch, and they came out. Then you had to put them through a sorter, and then you sort them all out into a couple of other stacks, and you bring them over to a counting machine, which could then read them and do some additions and print. So he had to break the problem up into separate, completely independent pieces. So he did it successfully, and he wrote up this prime factor algorithm. The reference is 1953. It was a book on, you know, the best source of some of these is the recent reprint that I have in the ASSP magazine on the rediscovery of the FFT. It was originally published at a history conference of the ACM. Well, so he had, Thomas had that, and now we call the prime factor algorithm the Good Thomas algorithm. We don't mean it's good. It's named after I.J. Good, who had done it before, and Professor Thomas, who independently found it in these old papers. Well, there are many other things we can say about this. John, would you like to add a few more to that?
Well, let me say just a couple of things. One, there is an Orwellian tinge to all of this, because in what year did the paper about things going back to Gauss finally appear? Namely 1984. How could you be more Orwellian? The other one is, have we managed to confuse you enough so you don't believe the FFT was ever invented? I get the impression from Jim that there are people who feel somehow there ought to have been an orderly progression of things, and they'd really like to understand what that was. What I have to tell them, I think, is there were so few steps involved here, there couldn't have been an orderly progression. And so you have a lot of people who independently got as far as doubling and didn't have a computer that made them interested in doing larger transforms. And then you have people who did or would have. There's also the name of Lloyd Welch, who was an independent inventor, somewhat later, I think, than Good. If I hadn't been there, other people would have invented it. The only question is which year. So we seem to have done a reasonable job here, and we're a few minutes ahead of our official closing time. So I would be willing to entertain questions if there are any. There's a lot of people to take questions from, but maybe we can make it work.
Oh, there's a question here. Yes.
Yeah, I was just curious, have you guys done research on checking on partial cycles if you didn't get a full cycle and you wanted to do some kind of FFT analysis on frequency, but given less than a full cycle? Have you guys done work on that?
Well, even if you had a full cycle, you should be worrying about end effects. You should be windowing the data. Now, you have a real problem about aliasing in this situation. All I can do, I think, is direct your attention to various papers in first two volumes of my collected papers, and the references in them. You need to understand the name of the game fairly well, and if you understand the name of the game, then I think you'll understand what you can and can't do, and how to do the things you can do. But you do need to understand the problems that go with having a finite piece of data. You need to understand the problems that go with having data only at discrete values. That's not an immediate answer. It leaves you a painful amount of reading, but it may be the best way to get there still.
Another question?
Yeah. At what point was the FFT first conceived to be useful for fast convolution, overlap add, overlap save?
Well, that's a very interesting question, because I didn't think of it at all.
Repeat the question.
Yeah, I'm sorry. The question was, at what point did anyone mention computing convolutions via FFTs? Now, there were several. The very important one was Gordon Sanday. I didn't think of it myself, and Gordon's paper, which he wrote almost simultaneously, which didn't get published, he gave it at the Arden House, was to suggest that you could use this for covariance functions. That was a very important one. The other one who saw it independently was Tom Stockham, because he was computing large convolutions, and he suddenly said, oh, it's an n-square calculation. I can do that with FFTs now, and n log n. I think you said you didn't think of that at first either.
No, I think Gordon and Tom Stockham are the people to mention. And as I know, the first place it was emphasized in the literature was the Gentleman and Sandy paper called Fast Fourier Transforms for Fun and Profit.
Yeah, but the other one at Arden House was done before that.
I know. I say the first one
in print, or yeah, I guess.
Well, no. Their paper was published in '66, the year before Arden House.
Yeah, but I think Gordon wrote the paper before that.
Yeah, well, he wrote something else before that wasn't published.
That's the one.
The historians can work on this one. Well, the people who want to read a paper can read the Gentleman and Sandy paper.
Well, the story I heard, he wrote the paper and he came to your office and he was going to talk to you about publishing it. And then someone said, well, there's a paper on John's desk already from somebody in IBM. So it's almost simultaneous. There's another question. Yeah. Yes?
Well, efforts have also been made in terms of speeding up Fourier transform computation using methods other than the DFT. In particular, I heard about the Winograd Fourier transform approach. For some reason, those approaches don't seem to have taken off as much as the FFT approach. And I would like to hear what your comments are on that.
Oh, the question is, I don't know if everyone heard it. I didn't hear all of it myself, but I heard the Winograd Fourier transform, and I guess you want to know what role it plays. Yes,
I would like to know why it hasn't become as popular as the FFT approach developed by you and others.
There are several reasons. One, he reduces multiplications quite a lot by the Winograd methods, but there are more additions and the program becomes more complicated. But actually, in large FFT programs, which I've been involved in at IBM in their engineering scientific subroutine library, the program actually uses the best features of both and combines them all. And those methods aren't published, but Sid Burris's prime factor algorithms papers describes how both algorithms can be made to work together. You use each one or the other when it's of advantage. That is, you can take n, factor it into all its factors. You can do some of the factors with Winograd algorithms, some of them with FFT, and you can even nest them and combine them in lots of ways. That's why it keeps us all busy. There's so many different ways of using this. Does that answer the question? Yeah, by the way, in recent machines, though, in our vector machine, you end up, it ends up that the additions and loads and stores take one cycle, and multiply add also takes one cycle. So it gives a little less incentive for using the Winograd algorithms. The multiplications are not relatively as expensive as they used to be. Are there any other questions? Well, if there
I hope and trust that the one-page souvenir sheet will be available just outside the door for those who want to take the trouble to get it.
Thank you.
Outside the door?
You want outside the door?
Yeah.
Okay.